Okay, I make it 3:30, so next speaker is Michael Mossinghoff, and he's going to talk about oscillations in sums involved in Liouville function.
Thank you, Roger, and I'd like to thank the organizers for the opportunity to speak here today and for putting together this terrific conference. I'm really enjoying it. So today I want to talk about some joint work with Tim Kirkwood at Australian National University, and I want to talk about some problems involving the Liouville function. So let me just remind you of the Liouville function in case you're not familiar, but this is the completely multiplicative arithmetic function defined by setting lambda p to be minus 1 for each prime p. So if I wanted to compute lambda, say 500, you might merely need to count the prime factors of 500, including multiplicity, and use that number as the parity to indicate a plus or minus 1. So this comes up with some frequency in analytic number theory, owing mostly to this representation of the Dirichlet series for zeta of 2s over zeta of s, if the coefficients there are given by the lambda. All right, so I want to talk about some problems involving the Liouville function that have come up. And the first is one that was investigated by Polya early in his career with this kind of generically titled manuscript here, Several Problems in Number Theory. But one of the problems he considered involved this function called L naught of x, which is simply the sum of the Liouville function values for all n up to x. And in fact, his main result with respect to this part of the paper was the following. If q is a prime number in 3 mod 4, and if q adjoins square root minus p as class number 1, then L naught has to vanish at a particular point. And of course, when he found this, he computed lots of values of L naught to see if some vanished, and it did vanish at some point, but kind of maybe the amazing thing was it was never positive past 1, so it skewed negative. And he said he tested this up to about 1500. So sometimes in the later literature, this question is does L naught remain negative? Sometimes that's called Polya's conjecture, but really he never really conjectured this, he just noted this as an implication. And while this is an important, this will be important because we're going to follow, I think, some of the earlier talks this week mentioned this, if this held for all n, so if this would remain negative. So sometimes that's called Polya's conjecture. I prefer to call it Polya's problem. That's how not that can change something. So maybe a little bit more news on that in just a minute, but let me say a little bit more about the connections with the Riemann hypothesis here. So the Riemann hypothesis and the simplicity of the zeros would follow more generally from the existence of just a positive constant c, so that this normalized L naught function, just divide out by the square root of x, if that never crossed a particular line. There's nothing special about the x-axis. Okay, pick any line you want. Okay? So Polya's problem then is just that's zero. From the earlier talks in this session, we talked about some analogs of this function with the Mobius function. And of course, this is the well-known Mertens problem. We can make sort of similar statements with the Mertens problem. And the question is if you make the corresponding sum m of x just being the sum of the Mertens function up to x, okay, is that bounded? This would also give you the Riemann hypothesis and the zeros and so forth. But I thought I would bring up one connection to some early work of Krishna's in his, I think this dated to his PhD work, in fact, so he has some papers from the early 80s, which looks at asymptotic behavior of similar functions involving the Mobius function. And I'm not going to say much more about this here, but it's beautiful work. One paper investigating the sum of the Mobius function for all n up to x whose smallest prime factor is bigger than some parameter y, and a companion paper that investigated the sum where the largest prime factor is bounded above by something by a parameter y. So I thought it was fun to have this connection to Krishna's work. But let me talk about one other problem that was investigated by Turan. In the late 40s, he investigated this weighted sum of the Liouville function, so sum of lambda n over n. And in fact, earlier in the session, we saw the corresponding sum with the Mobius function. And I won't go into what Turan was investigating in this paper, but he noted that L1 of x was positive up to 1,000 as far as the computed n. And from here, you could get the Riemann hypothesis, the zeros as well. And sometimes in later literature, this is called Turan's conjecture. But not only did he not conjecture it there, he actually wrote another paper where he said, well, I did not conjecture that. So it's very clear that it's not Turan's conjecture. So maybe in fairness, Turan can call this Turan's problem. Does L1 affect the chain of sign? Right. So, and well, you can do the same trick as before. You could bound the oscillation of L1 to X root X. That would be the Riemann hypothesis in this case, zeros. So all this sounds like an interesting line of work. Oh, let me give you some pictures first before I do this. So here's a picture of the L naught function. This is the x-axis up on top here. The scaling on here is kind of funny. It says in units of 10 to the 7, so that's up to 3 times 10 to the 10. Okay, so you can see the oscillation behavior, but it's never quite crosses the x-axis in this range as far as the resolution of this picture goes, at least. And here's the Turan oscillation down here, and now the x-axis is down below. It's the same scaling down here. It's up to 3 times 10 to the 10. Okay, so a lot of oscillation, but never quite crossing in this range. All right, so let me list some prior results on this. Okay, so Hazelgrove proved that that both of those functions, L0 and L1, change sign infinitely often. And I'll say something more about how that was done in just a minute. Lehman was the first to find a particular crossing, okay? And Tanaka was the first. Was the first to do an exhaustive search up to that point. He found one sort of nearby. That's actually the first point past one where L1 is positive. A prior paper of mine with Peter Bowen and Ron Ferguson found, for example, that L0 is fairly large, this number, and that L1 is actually first negative at that point there, that number there, that's a 14. That's the first time where L1 hits. So now, all this sounds like an interesting way to investigate the Riemann hypothesis, but the picture sort of changed in 1940s with the paper of Ingham's. We showed that bounded oscillation implies more, right, than just the Riemann hypothesis and the simplicity of zeros. So suppose you did cross. Suppose there was a line that you never crossed. Okay? Suppose L naught of X over root X minus C had constant sign at some point on. Okay? Then he proved that it would follow that there are infinitely many integer linear relations among the zeros of the zeta function, the ordinates of the zeros of the zeta function on the critical line. Okay? And there was kind of sort of there's no sort of prior reason to believe that this might be true. This is sort of cast out. This is a method to establish the hypothesis. You can do the same thing for L1. So I want to talk about a couple of key ideas from Ingham's paper here. This is what I want to talk about. I want to talk about bounding the oscillations in these things if we can, or showing that the oscillation is large. Okay, so let me define first A naught, function A naught, to be, well, simply the scaled version of L naught, and I'm going to replace the X with an E to the U just for convenience. I'll let F naught denote its Laplace transform, that ends up having a nice form like this. And now, well, the F naught has some simple poles, so you can see when it's 0 there, and certainly I'll see them going up the critical line with 0 to the zeta function there. So I'm going to define F star to collect all those simple poles together, along with the residues. Okay? It's what's preventing F naught from being nice and analytic, okay? Under the assumption of the Riemann hypothesis.
That's not uniquely defined.
I'm sorry?
Is that uniquely defined?
Let's see. Oh, well, when I do write it like this, I think
oh,
this one.
Then
Okay.
I can see.
Oh, yeah, I see. Yeah, so, yeah, that's right. What I said was it's not usually defined, but now it is. Okay, so I'm going to take that one. Okay. That's right. Okay, so I'm just collecting those residues together. Okay. And then, well, Ingham then computes the inverse Laplace transform of that interesting part, that F star. Okay. And, well, a wave function has to come along for the ride here for technical reasons. Okay, this kernel function comes along. But here's kind of his main theorem that comes out of this. He wants to show, that this gets large. He says, well, it's enough to show that this gets large. Okay, this is that's this inverse Laplace transform above. And this one's easier to work with. That's just a finite sum here. All right, and if I want to show that this thing is large frequently, I just have to show that it's large just once. And And this is what Hazelgrove did. And we just found a point evaluation of the B naught star, which was positive, and that was enough to show that the A naught would be positive. And from this, you can see where his linear independence comes from, because, well, the sum of these residues is infinite here. And so, well, when you look at this sum right here, we could make this thing large just by, or, well, maybe we could magically arrange all of these complex numbers to sort of point in the same direction. Okay, so if we're multiplying by this complex number of unit modulus, but, well, if those gamma n's are linearly independent, well, then simultaneous approximation says that we can pick a u so that the arguments of these things fall all more or less in the same direction. We can make them all pull positive or make them all pull negative. This is kind of the idea. All right, so I want to talk about quantifying the oscillations in this. Okay, what can we say about making these things large? Okay. All right, so Anderson and Stark had some results on this in the early 80s. Where they noted essentially that they knew L naught of n was large in one place, we'd have to get large again. Okay? And so using Layman's data from his paper, they showed that, well, L naught of x would have to be bigger than 2% of root x infinitely often. And using the paper from the data from the paper I mentioned earlier, you can improve that to about 6%, and you can also prove something on the low side too. Okay? Down to minus 1.4 times root x. All right, so I want to talk about another approach, and this is an approach that was pioneered by Carol Diamond and Roswald and some others. But let me remind you first that Ingham's result says essentially that if the zeros of the zeta function are linearly independent, then that L naught of x over root x is unbounded. Okay? So this approach from Roswald, Diamond, Anderson, Stark, Bateman, and others. Essentially says, well, what if we could weaken the hypothesis here? Maybe if we weaken the hypothesis, maybe we could obtain a weaker conclusion. So what do I mean by a weak independence, a weak hypothesis? By weak independence, they say, well, if maybe we should make that if a linear relation exists, then it has to involve a large coefficient. That will be our notion of weak independence. Okay, so what does weak conclusion mean? Okay, well, instead of weakly unbounded, maybe that means sizable variation. All right, so maybe weak independence implies sizable variation. That's kind of the idea. So Trojan and Best just last year came up with an effective method using this idea to improve the bounds of the Mertens problem. Okay, so what I want to do is talk about using this method on some of these Liouville properties. All right, so let me say more specifically what I mean by weakly independent. Okay, so think of gamma be a set of positive real numbers. These will be zeros of the zeta function. Okay, and I'll let gamma prime be a finite subset inside of range inside of range 0 to t. And I'll say that gamma prime is independent in gamma relative to t if the following two conditions work. And this says that I think of gamma prime as my favorite set of zeros inside gamma. Right? So this says that there's a linear relation among my favorite set of zeros, and all those coefficients are small. Well, then it's trivial. The other condition is maybe a little more complicated to write down, but all it's saying is that I can't use my favorite set of zeros to make one of my non-favorite zeros, okay, without using a giant coefficient. Okay, so this says that if gamma star is any zero, it might be my favorite or it might not be, it's just inside of that range. And I have a linear relation among my favorite ones that makes this gamma star one, okay, and the coefficients are small. Okay, then the only way that can happen is the obvious way. Gamma star was one of my favorites, and its coefficient was 1. Everybody else was 0. Okay. Right, so there's no relation among my favorites, and there's no way I can use my favorites to make a non-favorite. Okay, so that's all that's saying. Okay. So the result of Anderson and Stark says this, for example, if G is a continuous real function, given the Laplace transform has an element of continuation back to 0, except for some simple poles that we can take care of. Okay, we'll write down the residue here. And I pick a subset inside gamma called gamma prime. And I can prove that's we can show that's n independent. Then you can show that the original function g has large oscillation. It has to get large and it has to get small. Okay? And this structure here is a lot like the structure of what I had before for Ingham's result. That's the sum of the residues here. That's a kernel function that comes in here, this wave function. The only thing that's new here is this n over n plus 1. All right, so the price of being n independent was just reducing that bound by a bit. And it's not that much. All right, so that's what we want to do. So here's the plan. We want to apply this to our function a naught, okay, which is just our scale delta. Okay. All right, I'll think of gamma equal to as the locations of the zeros of the zeta function. I'll pick a subset gamma prime inside. Okay, and then we'll have to figure out what n is. All right, so the strategy to find n is to create a number of lattices. And the idea is that you want to show that if gamma prime is n dependent with respect to t, then some lattice is a short vector. Okay, and then we need one other piece that says that these lattices can't have short vectors. Okay. All right, we'll pick an n at the end of the day so that none of those lattices can have a short vector. This is kind of the broad strategy here. So I'll give you a little more detail here. So we'll construct our lattices the following way. I'll pick a parameter b. This is bits of precision. All right, just for convenience, let me note x in parentheses as the integer nearest x. And then given gamma prime, we'll create a lattice with the following basis. Just take the n by n identity matrix and attach this giant number on the end here. So this is huge number times ordinate of n0 of zeta, okay, rounded to the nearest n. All right, so now suppose gamma prime is n dependent. Suppose something bad happens. Okay? Then a vector is going to have a short a lattice is going to have a short vector. Okay? All right, so if it's n dependent, then one of the things that I said couldn't happen does happen. All right, let's say it's the first one. Okay? All right, so if that happens, then that lattice that I put up at, just on the last slide there would have a short vector. Okay? The vector whose length is bounded by this. Okay? All right, so if there's an n dependence, then there's a short vector. And you can run through the other cases too. If there's an n dependence, then you'll have a short vector in a lattice. Well, the other lattices will have one more column. We'll need the gamma star in there too. All right. So then we need one more piece of this, which says that, which will allow us to say that a particular lattice doesn't have a short vector. So that's given by this proposition. You can find this in the book by Bremner on lattice reduction, for example. If you have a lattice with a given basis, you just compute its Gram-Schmidt orthogonalization, then a lower bound on a non-zero vector in your original lattice is the shortest thing in your Gram-Schmidt orthogonalization. Just do regular Gram-Schmidt. Now the problem is if you run Gram-Schmidt on a generic basis, you'll get a really tiny bound out of this. It won't work very well at all. Okay, so you need your basis to be sort of more orthogonal for this to work. Okay, so you just have to run your basis through LLL before running this and doing the Gram-Schmidt. Okay, then it. All right, so here's the method. All right, so we'll choose t. Okay. So, we'll pick a number n. Okay? N will be the dimension of our lattice, and n will be the number of favorite zeros of the zeta function. M is the total number of zeros up to height t. All right, so gamma prime will be my favorite n zeros from these. So what does favorite mean? Favorite means large value of residue times wave function. Okay, I want the biggest ones. Okay, and then we have to test a bunch of lattices. So one is the one that I showed you. The other m minus n is where you take one of your non-favorites and toss it in the center column. Okay. Run each through LLL. Run each of those through Gram-Schmidt. Each one of those you'll be able to figure out your n value. Okay, that you want to pick. Pick the worst n value among all of those. Okay, and throw that into the energy start, and you got it. All right, so there's more choices. There's some different wave functions you can pick. Okay, there's some freedom there. You can pick how many bits of precision you have to work out. That's going to affect the runtime. There's a parameter in LLL that's usually called delta that affects how hard LLL is working. So there's some decisions you have to make, okay, when deciding how to compute these things. But now to tune this, say we want to show that L naught of n is greater than root n infinitely often. Okay, there's actually lots of different ways to compute this, and there's different ways we can choose our parameters. We want to choose our parameters in a way that's going to minimize the total time. All right, and well, I guess roughly we could pick, if we pick n to say, you say 240, okay, well then each lattice that I look at is, well, fairly small, only 240 dimensional, so they run pretty quickly. But in order to get 240 good enough zeros, I have to go up to look at the first 5,000 zeros, okay, before I find 240 good ones. If I pick 300 zeros, okay, then each lattice is larger, but I don't have as many to look at. Okay, so there's some kind of perfect, well, happy medium here somewhere in the middle. This is the number. This is an estimated number of bits of precision that we need. Okay, the result we want. This is an estimate of the constant that would come out at the end. We want it to be bigger than constant root n. Okay, we want to leave a little bit of room at the end here. And that's an estimate of the time needed, and the units don't matter here so much, but n equals 250 looked like it was about right.
There's hours at the end.
What's that?
Sorry, time is measured in what, hours?
Yeah, this was days.
Okay.
This was days on one machine.
That's a lot of time.
So this would have been days if I just sat it on my desktop, okay, which I was not going to run on my desktop. Okay? But this suggests the parameters to pick. We haven't picked delta very large. We didn't need B quite as large, which helped out once we got down to actually test these things. But this produced, this ended up being almost 3,500 jobs at a computation center in Western Canada. Okay, so I could run the whole thing in a week or so. Okay. And it produced an n value of about 2,500. Okay. Right. So then at the end of the day here, we have the following theorem. So each of the following inequalities holds infinitely often. So 1 L naught is less than minus 2.37 root n infinitely often, and it's bigger than 1.02 root n infinitely often. And there's some nice symmetry that happens for the L1 function. It's infinitely often less than minus 1 over root n. Okay. All right, something similar on the positive side. But with that, I think I'll thank you for your attention, and I'll also wish Krishna a happy birthday. Right.
Questions or comments? No, well then, that's the thing.
I know that the next talk starts at 4 o'clock. The gentleman who the video camera is there, he has to leave also at 4. If any of you would like to express your opinion on the movie, you can tell him that's being recorded by the producers of the movie, and they want to show this as sort of like a promotion. So if you want